phase of water will be liquid. So you can cook in a liquid which has a higher temperature than 100 degrees, water. And that speeds up the cooking process. So at the end, you will need less energy. That's the principle of the steam cooker. Yes, you can cook in a liquid water above 100 degrees Celsius because you press it together so that it's not transferred into the steam. But because the pressure is pressing the water molecules back to the liquid. You can try to imagine like that. And if there is one atmosphere, it's more easy to get free in the gas phase. But if you have high pressure on it, they press it back to the liquid. It's not so easy to get free and to be transferred into steam. The good point is we can cook now our potatoes at 140, 150, whatever degrees Celsius, and not only at 100, and in a liquid.
Excuse me?
Yeah.
I need to make some corrections. At first, oh yeah, the unit of R is joules over Kelvin and mole.
Yeah, I forgot the Kelvin, yeah.
And it's not called Rydberg constant, it's the ideal gas constant.
Yeah, but I think it's another name. Mr. Rydberg found it.
No, the Rydberg constant is related to the atomic spectra.
Okay, maybe you're right. Okay, then cancel it. Call it ideal gas constant. Sorry. But I'm not sure. I will look it up. Okay, call it in general ideal gas constant. And here the Kelvin is missing. More, Joseph?
No, thanks.
Thank you. Okay, this ideal gas law is very important. So there are some different situations. So situation, let's talk about the temperature is constant. When T is constant, and we are always looking to one specified number of mole. What does it mean? N is constant as well. What does it mean for the product PV? Oh, so that means PV is constant. There is a question, yeah? The R is the letter for it. And that's why I thought it's the Rydberg, but maybe Joseph is right. So T and N is constant, then means PV automatically is constant. If, for example, another situation, P is constant and N is constant, what does it mean now? We have P is constant, N is constant, then we have the volume is a constant times T. Must be. If volume is constant and N is constant, then it must be P is a constant times T. Yes? Again, what? That one? That means the same as here. It's just these double brackets. when N is 1 mole, then we can see the volume is RT over P. And let's talk about standard conditions. Standard conditions always means P is 1 bar. So standard condition 1 bar and temperature is 293.15 Kelvin, which is 20 degrees Celsius. What is the volume of 1 mole of gas in the standard conditions? Yes. So the volume of 1 mole gas at standard condition in this case is 22.4 liter. And this is not depending which type of gas we have. It could be water molecules, it could be CO2, it could be hydrogen, it could be carbon monoxide, it could be methane molecules, totally the same, because the volume of the molecule itself, it's very, very, very small compared to the 1 liter box. Pressure is important, temperature is important, but then for 1 mole of gas, 22.4 liter volume is needed in standard conditions. Is there a question? Any question? If there is, please ask and try to be focused, not too loud in the audience, because it's quite difficult in front to speak when everyone is talking in the audience. Oh, now, well, we are talking about gases. Another point is the sum of the pressure of different components in one volume. When you're talking about the pressure of maybe now talking about a mixture of CO2 and oxygen. Those are a gas in standard conditions in 1 liter volume. What is the overall pressure in there, or how can we calculate the overall pressure? Therefore, we need another parameter. We call it partial pressure of the components. So let's say we have a mixture of O2 and N2 and CO2. That is the main components of, or some of the main components. We have additionally noble gases. Do you know the concentration of these elements in the atmosphere? What's the concentration? So the concentration now, sorry, is now in percent. We talk about percent. So we have here mass percent or mole percent or volume percent. We now talk about volume percent, liter per liter. So the volume percentage of oxygen in atmosphere is 21%. The volume percent of nitrogen is about 78%. The volume percentage of noble gases, you know them as well. No, noble gases, it's nearly 1, so 0.96%. And for the volume percent of CO2, again, please. Yeah, 4.2, which is similar to 420 parts per million, ppm. So this is our atmosphere, and we have, let's say, one atmosphere, 1 bar pressure, but which is the normal conditions. When we have to calculate now the pressure related to the participation of the different gas molecules, then we can say the sum of the pressure for each of them is in total is the overall pressure. So the pressure in total, P total, is the pressure of oxygen plus the pressure of nitrogen plus the pressure of noble gases plus the pressure of CO2. We do not talk about other components in the atmosphere. We have hydrogen little, we have methane little, we have very many other, but very low concentration. So we do not calculate. Ozone as well, but it is a very low concentration. So the sum of pressure for more than one type of gas moles is in a defined volume is like this. So the P total is always the sum of all partial pressure of the sum of X elements. And for X is 1 to X is I, when we have I different types of gas molecules in our volume. So the total pressure is the sum of the partial pressures. The total pressure is the sum of the partial pressures. It's not important which type of gas molecule we have. Each of them contribute to the total pressure in the same way, because the size of them is small compared to the volume we are looking to. If you, of course, look to 1 nanoliter, then maybe even the size of the molecules plays a role, but that's not the way how we do it. A nanoliter, we can't see. So you talk about liter. That's why we say it's the ideal behavior. Of course, in reality, if we'd like to do it very exactly, we have to calculate the interactions between the different gas molecules. And then it's not exactly an ideal behavior. But for the most calculations we have to do, and we have to do it quick and roughly to check out, the ideal gas law helps. So in an ideal gas, what does it mean? we have a component A in the volume with the number of moles of the component A, and R and T is constant. We look to one special temperature, and we have one volume. And we have a component B in the same volume, but maybe more or less moles of component B, B. RT is the same. So if we now calculate pressure of component A, partial pressure, the partial pressure is pressure of component X. Now we add the X for the name of the component, plus the partial pressure of B is NART plus NBRT. Or it is NA plus NBRT. So we can calculate the partial pressure in a specialized volume and an exact level of temperature when we know the number of moles. In an ideal system. Well, I'd like to talk with you about one example, which is the phase diagram of water. The phase diagram of water, we need two axes. The y-axis is the pressure level. And the x-axis is the temperature level. So we have a PT diagram. To the right, now let's write the temperature scale in degrees Celsius. We can convert it in Kelvin if we want. And the y-axis is the pressure, P, now in bar. We know a level of about 1 bar. It's not exactly 1 bar. It is 1.013, 1.013 bar. This is the normal pressure at standard conditions. Do you know the melting point of water at standard conditions? 0 degrees Celsius. So the melting point is 0 degrees Celsius. Let's say it is here. And then here we have 0 degrees Celsius. This is the melting point. So this is a fixed point. Do you know the boiling point at 1 bar, 100 degrees Celsius? So let's say the 100 degrees is here. This is the melting point. The boiling point, sorry. Now, there is one speciality in the phase diagram of water. This is the so-called triple point. Did you already hear about the triple point of water? there is one point where we have the three phases. We have the phase ice, water, and gas. And that point exists for water, and that's called the so-called triple point. And this is at a pressure of 0.006, I think. So here 0.0061 bar, so very low pressure, and at a temperature level of 0.01 degrees Celsius. Here, this is the triple point of water. Now, when we try to draw our graph, we start here at the absolutely point of 0. This is here minus 273.15 degrees Celsius. That's the absolutely 0 point of temperature. And then we come up with our curve to the triple point. From the triple point, we have here the way up where it's like this. And we come up to the boiling point here. And there is one other point, which is called the critical point of water. Did you hear about that? The critical point of water. This is where we have a phase, we call it's like a plasma. So we have a critical water, and this exists at quite high pressure. It is 220.5 bar and temperature 374 degrees Celsius. This is the so-called critical point of water here. And above, we have, we call it a fourth phase. It is a kind of plasma or critical water. So here, from the boiling point, we have the curve coming up to the critical point. So this is the triple point. This is the freezing point. This is the boiling point. And this is the critical point. Now let's go on with interpretation. What is the phase of water here? Solid. So here on the left side, low temperature, relatively low pressure. Here, water is solid. What is the phase here? Is it liquid? So here we have the gas. Because when we increase from 0 degrees Celsius temperature to 100 degrees Celsius, then it's transferred into gas at higher temperature at that pressure level. If we have a higher pressure, you see the boiling point increases. When the pressure is higher, the boiling increases. So here, this is gas. And here, it's a liquid. And this is, of course, the situation for water. Well, I think you know the transformation of liquid water into a gas. How do we call that process? Vaporization, I think. Vaporization. Yeah? Vaporization. So here, when we cross this line from the left to the right, that's vaporization. When we do it on the other way around, back, yeah, we call it condensation. That's condensation. When we transfer from solid to liquid, what's the name of this? Melting. And do you know the name for the freezing? Yeah? Vice versa, it's freezing. And now the transformation from solid directly into gas, from solid to gas, this way. Yes, sublimation. That is sublimation. And the way back, desublimation. Yeah? The name of the curve here, this curve we call sublimation curve. This curve we call the melting curve. And this curve we call the boiling curve. Or the vaporization, another name. Curve. So, well, of course, my axes are not normalized. Huh? So here, of course, this is not really the right scaling. And that's why I put here a break in there. You should be aware on this diagram. It could be a question in the exam to draw it, because water is the most important liquid in life. And you should be aware on that. Of course, we will have maybe in the engineering and industry a lot of different liquids and phase diagrams, more complicated. We do not talk about them, but water is essential. So you must know temperature scale, pressure scale. Think about the units. Without units, you won't get the point, because we don't know what you're talking about. Apples or sherries or whatever. And then, of course, there are a few points to remember. One is the freezing point, the boiling point, then the triple point, and the critical point. Then you can start drawing the curves. It's not a big deal. You just have to know those points, those four, and the values for them. New may be critical and triple point. The others are standard knowledge, I think. And then think about where do we have solid, liquid, and gas, and how are the names of sublimation, desublimation, the transfer. Here, melting, freezing, vaporization, condensation. I think you all heard about, but try to put it in a figure like this. Engineers have to work with such figures and knowing about them. Very important. So when we try to look again to our steam cooker or to an evacuated flask, if you evacuate, that means here now you reduce the pressure. What does it mean for the freezing and the boiling point? When you now reduce pressure, the freezing point again, you go down with the pressure. We go down pressure, so both freezing point will, it will be higher. Yeah, you're right. Sorry, I did my mistake. So the freezing point will increase, but only little, and the boiling point will be reduced. If you increase the pressure, the boiling point will increase and the freezing point will decrease a little. This is slightly hanging to the left. If you have a fixed volume and you increase the temperature, but you do not increase the volume, automatically pressure increases. So if you are up on the Mount Everest, what are you expecting to the boiling point? The boiling point will be lower because the pressure on the top of the Mount Everest is lower. If we have a lower pressure, the boiling point will be lower. So you can cook your eggs at maybe 80 degrees Celsius. So, and if you are now trying, maybe in the lab, you have to try to boil a liquid which has a boiling point of 350 degrees at normal conditions. Yeah, so just suck out the gas, reduce the pressure, the boiling point decreases, and maybe you can boil it at 100 degrees. So evacuation, so in an evacuated flask, the boiling point is below 100 degrees. Always talking about water. The behavior, of course, is similar to other liquids. The values are different, but the behavior just in qualitatively manner is similar, not depending on the type of the liquid. In an autoclave, or a steam cooker, the boiling point is above 100. Degrees Celsius. So heating up the water in the steam cooker, what happens? We have our steam cooker, which is now closed, airtight. And we have here a kind of valve when the pressure is getting too high, that there is no dangerous situation. Now we have here a flame. I just have a candle, but of course it might not be enough. Just to symbolize, we heat it up and we have water in there. What happens first when we heat up the water in our closed steam cooker? Reduces, increases, yeah, because a few of the gas molecules, water, steam is built, and we have we call it vapor pressure of water. Of course, when we have a hot water, more molecules are already transferred into the steam phase compared to cold water. Not all of them, not everything is cooked, but the higher the temperature, the more molecules are already transferred into the gas phase. That is what we call the vapor pressure of water. So when we heat it up, more and more will be transferred into the gas phase. But what happens when temperature increases, then in the gas phase of our cooker, pressure increases. And when the pressure increases, when we look to the phase diagram, the boiling point increases. That's the behavior, and that's why we have a liquid water above 100 degrees Celsius. Okay. Any questions? That is really important because you will need it in different phases of your studies and maybe even in your professional career. If there is no question, let's have a break now. 15, if there is one? No, we're here. Yeah? I tried to explain it before. When you have, let's look to that, to that example. Now you increase the pressure. The pressure presses is a pressure on all the molecules. So the freedom to be transferred from the liquid phase to the gas phase is reduced because the pressure, the atmospheric pressure presses them back to the liquid. That's the figure I have, and that's reality. Higher pressure, it is more hard to come out of the liquid. A liquid is incompressible. A liquid, you cannot decrease the volume via pressure. It's incompressible. A gas, you can compress together. In a gas phase, the molecules have a lot of space. In the liquid, they are more close together. And in the solid, they are fixed on fixed places. They cannot move. In the liquid, they can move, but they are nearly close together. We talked about hydrogen bridges. In the gas phase, we don't have them. They are far away. They are far away. Each gas molecule is free. In the liquid, they're close, and in the solid, they are fixed in the ice crystal. They cannot move. High pressure doesn't allow them to come out into the gas phase. Other questions? Yes? I didn't understand, sorry. Can you repeat? Yeah. It will be a gas. So you can look to that. When you evaporate, you are here in the gas. That's a gas as well. You're in the gas. Yeah, if you heat it up, it's depending on the pressure level, if it is a gas or a liquid or whatever. It's always combination, temperature, pressure, volume. If you just say the volume is fixed, we always look to 1 liter. Then you have the 2 parameter, pressure and temperature you can play with. If you even, you can even increase the volume. Yeah, when you pump up your bike, then of course it is increasing the volume a little. But it's getting warm even. If you do it very strong, the pump gets warm. Because then you have high pressure in it and the volume isn't increasing in the same speed, then it's getting hot. Sometimes if you have a metal pump, you can't hold it. It's getting quite hot. Other questions? Okay, then we meet again at 47 past 3. Okay. Back again. Now we talked quite a lot about the parameters, the units, the phase diagram of water. Now let's go on. Before we are really able to talk about chemical reactions, we need a few definitions or a few settings. Another one is related to the energy level. Maybe you heard about the terms endothermal and exothermal. What is endothermal? Exactly. So an endothermal reaction and energy is needed. We have a parameter to measure it. It's the enthalpy, or the difference of the enthalpy, delta H. And if the delta H is above 0, the unit is kilojoule over mole. That means we need energy. We need an invest of energy. That's an endothermal reaction. Enthalpy. Enthalpy is the parameter in thermodynamics. An exothermal, sorry? When we release or when energy is delivered via the reaction, it's exothermal. Exothermal energy is produced. Now the difference in the enthalpy is below 0. Kilojoule over mole is the unit. Joule, you know, is the unit for energy, and we always normalize it. We say we look to 1 mole of the reactants. We'd like to have another view on water again, because this is, as already mentioned, the most important molecule in life, one of the most important. We draw a graph. Again, to the right, we have the temperature in degrees Celsius, kilojoule per mole. And the y-axis is now the enthalpy in kilojoule over mole. Or we say the delta of the enthalpy. And we have 2 points where we'd like to look to. One is 0 degrees Celsius, and the other one is 100 degrees Celsius. Now we say fix at 1 atmosphere. ATM, 1 atmosphere or 1 bar pressure. We are standard conditions related to the pressure. Now we come from a temperature below 0. What is the phase of water? We are talking about water, normal pressure, ice. So we have ice on this side and we heat it up. So it is ice. And of course, we come from minus 100 degrees Celsius, it's ice. So, but we heat it up. So we come from minus 100 up and we come up to 0 degrees Celsius. Here, now, what happens? At standard pressure, ice is melting. What does it mean now when we have ice and it turns into water? But as long as we have ice in the system, is the temperature increasing? It stays the same. So we invest energy in form of enthalpy, but the temperature doesn't increase as long as we have ice. It stays at the temperature level of 0 degrees Celsius. At the point when we have all of the ice transferred into a liquid, always talking about the ideal situation. Now what happens? We heat it up again. That means the internal energy, the enthalpy, increases. Enthalpy is the heat energy of the system. It increases up to 100 degrees Celsius. When we invest energy, we can heat up the liquid. But now we are at the point where it starts to boil. What happens here? When we have, again, the same situation, we have to invest energy until all of the liquid is transferred into steam. And then we can heat up the steam to any temperature. This is known very well. And well, when we invest here energy, this is melting. But temperature does not increase. But melting needs energy. And the difference here of the enthalpy, anyone knowing the enthalpy for the melting process? It's endothermal, but the value, do you know it? Endothermal means we have to invest energy. It's positive, and the value is exactly known to be 6 kilojoule per mole. So we have to invest 6 kilojoule energy to melt 1 mole of water molecules transferred from ice to liquid. The process here is called the vaporization. Anyone knowing the value for vaporizing 1 mole of water? The enthalpy needed for that is 40.7 kilojoule over mole. I just can recommend minimum this you should try to keep in mind. I know Mr. Heintaler sometimes asks that in later lectures. And this is a kind of standard knowledge. So the energy for melting and for vaporizing water. This both is endothermal. Huh? Upwards vaporization is endothermal. And melting is endothermal as well. The melting process needs less energy compared to the vaporization process. 6 kilojoule per mole, and here 40.7 kilojoule per mole. You can transfer it into kilowatt hours per mole, the joule into kilowatt hours. Do you know how? What is a watt? Is power, and 1 joule. 1 joule is 1 watt second. One kilojoule, of course, is 1 kilowatt second. In electrical engineering, they are very often talking about kilowatt hours. Now I'm asking you, 1 kilowatt hour is how many joule? No. When 1 kilowatt second is 1 kilojoule. Now 1 kilowatt hour is how many kilo or how many joule? Yeah. 3,600 kilojoule. Not over, it's 3,600. So vice versa, the vice versa is 1 kilojoule is 1 over 3,600 kilowatt hours. And so this is easy to calculate by your own. You should be really firm in units. It's more difficult to transfer it into calories or into other units because that are very strange numbers. You have to look it up. But this you can do by your own. So transferring kilojoule over mole into kilowatt hours over mole, sometimes you find these numbers in literature. You can do it by your own. The opposite process, now vaporization, here opposite is condensation. Condensation, is it exothermal or endothermal? Now that's exothermal. What about melting, freezing? That's the opposite of melting. Is it exothermal, endothermal? Exothermal. This is interesting. So just as an example, if you burn coal, let's not talk about coal, let's talk about methane gas. Burning methane gas, it's a combustion. Are you able to construct the chemical equation for the combustion of methane gas. What is needed? Oxygen is needed, so O2. And what is the product when we burn methane gas? CO2 and water, H2O. If we have two of them, so two. This is the combustion of methane gas. If this is fossil methane gas, we have CO2 as a product, and we don't like it because we are now in the times of climate change, and CO2 is the most important climate relevant gas. But this is exothermal. So this is an exothermal process. So heat is generated. That's why we burn methane, because we want to have it warm in our room. So we have a gas turbine to produce heat, to heat up our radiators in this university. Heat up water, and then the water is pumped through the radiator, and it is spending the heat to the room. So this is an exothermal process. Normally, the temperature level when we ignite methane gas is above 1000 degrees Celsius. What are you expecting of the phase of the water at that temperature level? Steam. So the water is gaseous. Now, when we have a chimney, we have to check that the water, of course, should not condensate in the chimney. Because when that happens, the water comes down in the chimney and you have a wet chimney. And that's not fine. So normally we have to check on the roof of on the top of the roof where the chimney, the top of the chimney is, it should have a temperature level above 100 degrees Celsius, so that the water is going out as steam. For CO2, no problem, it's a gas. But water can condensate. If we have an old heating technology and we just look to the heat value of the methane gas, we lose energy because we put out, or we press out hot water, steam, on the top of the chimney. In a new system, we try to use the energy of the steam. Therefore, we need another type of chimney where we can collect these liquid water and transfer it to the wastewater treatment. And then we earn more energy out of the same amount of molecules because we use the exothermal condensation. And the value of 40.7 kilojoule per mole additionally can be used. So this is a new way of trying to make the same system more efficient. We need another chimney. That is the upper heat value. The lower heat value is we do not care about the steam. The upper heat value is we use additionally the steam, the condensation energy of these process. So it's relevant to be aware on that topics because then we can optimize our processes, make it more efficient. So, well, when we now think on another example, the photosynthetic reaction. I always try to give you some examples to show the relevance of these more or less theoretical things. It's a lot of things I know, but we need it really in professional life. The photosynthesis. Do you know the photosynthesis, the chemical equation for the photosynthesis? CO2 plus H2O plus O2. Now please balance it. 6, 6, and 6. Is it exothermal or endothermal? It's endothermal. So this in that direction needs energy. So the energy comes from the sun plus energy, and the energy is light. And maybe you know the formula for the energy of light. How can we calculate the energy of light, of electromagnetic waves? H square or nu H square is Planck's constant. And nu is the frequency. So where is it coming from? From the sun. Sun invests energy to create these molecules. So from the left to the right, it is endothermal. Now, when we burn our biomolecule, it is just the vice versa process backwards. Is it endothermal, exothermal? Now it's exothermal. We need oxygen, otherwise it won't burn. We burn it and we create energy, exactly the same amount which has been invested before via the photosynthesis. So biomass is stored sun energy. It's automatically stored form of sun energy. We don't have to create batteries. We don't have to transfer anything into hydrogen, whatever we have to do. Biomass is by its nature stored sun energy. Biomass is by its nature stored carbon dioxide. Because as long as we do not burn it, this is stored CO2. In the former times, it has been a tree. By a photosynthesis, the biomass was created. And now it's stored sun energy and stored CO2. That's good. Because here we can use it on demand. First, it is a material, a desk. And when it's damaged or not working anymore, I demount it. The metal, of course, goes into the recycling. And the wooden part, we can burn it at the end of life to create energy. Of course, then we have CO2 again, but it is in a cycle. It's not as bad as burning fossil energies. So, well, let's have a look to the topics endothermal, exothermal. Again, we have here the enthalpy, the delta H in kilojoule per mole. And now to the right, I just draw it 2 times for the 2 different reactions. To the right, I say it is the ongoing reaction, the kinetics of the reaction here. And this is now the time, small t in seconds. The time in seconds. We say, okay, it takes a while until the reaction happens. And here again, delta H in kilojoule over mole. Now we look first on the left, we look to the photosynthesis. We make it as simple as possible, and we say our reaction starts at that energy level. That's the energy level of the molecules of the educts. So the educts are CO2 and water. These are the educts. And the product is these glucose, so our biomolecule, and oxygen. And of course, the energy level of the product is higher. So that is C6H12O6 and oxygen. Just to simplify, we do not split up in biomolecule and CO2, just products and educts. So the way of the reaction is now photosynthesis happens, sun delivers energy, and the molecules are created. No? We have CO2, we have only one carbon. Now here we have 6 carbon atoms via sp3 bond, covalent bonds fixed in this molecule. So we have to create a chain of 6 C atoms, the C6 molecule, but that needs energy, and this is the invest in the photosynthetic reaction, and it goes like this. The delta H of the energy difference of those two levels, this is what is stored in the biomolecule, delta H, and of course that's endothermal. We have to invest energy to create these molecules. Reality sometimes is not so simple because we have here an add-on. And this is what we call the activation energy. So EA is the activation. The energy for activation. That's EA. Now, that is the photosynthesis, and this is endothermal. The opposite now, when we burn it, we have exactly this level of energy. Now we come from the right to the left. Now these are the educts, so C6, H12, O6, and oxygen are the educts, and we burn it, and we will end up at the energetic level of CO2 and water. And now the way is the same, but back. Now we come like this to the level of CO2 and water. We say CO2 and water, there is no internal energy in form of chemical energy. Of course, heat, you can make hot CO2 and hot water, steam, whatever. Heat, you can have energy in form of heat, but not in form of chemical energy. There is no chemical energy in there because we cannot further oxidize it. It cannot be burnt. Here we have stored chemical energy. The oxygen is just needed for the process, but the biomolecule is stored energy. And now, again, this is the delta H of the molecules. And of course, we have an activation energy And that is not the baddest, because if this is not needed, the activation, my desk will start to burn automatically. If there is no invest before, of course, nature is driving the reaction automatically to the lowest level. We have oxygen in the atmosphere, so everything is here. The only point missing is to activate. When I ignite it, then a part starts to burn, that produces heat, is activating the neighbor molecules, and then it is an ongoing process. But we are happy that normally it doesn't burn. That's here, when we activate it, it starts to burn, and then it's an ongoing process, because then heat is produced, and that's enough to activate all the neighbor molecules. Some processes are starting immediately without activation. Here we need it. Yeah. Yeah, because it is the same level. Yeah. We come from here, of course, and then even here it has to come over this hill of energy levels. Yeah. So here, now this is exothermal. But this is not starting immediately. We need activation. That is called combustion. Here, the left is the photosynthesis. And the right is the combustion. Well, let's go on with a few main points in thermodynamics. We are really just talking about very short about that, not in details. You will have it, I think, once more in one of the later lectures. But we need it now. So the first law of thermodynamics. Yeah, you are on the right track. Yeah. It's more another type of the first law of the thermodynamics means the law of the energy conservation. This is the law of energy conservation. What does it mean? It means the total amount of energy in an isolated system is constant. That means the total amount of energy in an isolated system is constant. What does it mean? When we look to our steam cooker once more, if we do not heat it up, it's isolated. We say it's an isolated system. Huh? In reality, it isn't, because there is always a kind of heat transfer. There is no transfer of molecules because we say it's tight. But if it is more warm than the atmosphere, heat always is transported from the hot to the cold. If the environment outside, let's say this is 80 degrees in there, outside we have 20 degrees Celsius, so it's cooling down. You know? We can isolate it very good, then it stays hot for a longer time. The cooling process is needed more time, but at any time, it has the same energy or temperature level as the environment. But let's say we have an isolated system. In theory, that doesn't happen. That means in there, the amount of energy of the steam molecules, of the water molecules, of everything in total, this is always the same. It doesn't change. It's constant. That is the first law of thermodynamics. Energy can be transformed from one form into another form, but neither, and that's what you say, be created or destroyed. Energy can be transformed from one form into another form, but neither be created or destroyed. Again, looking to our isolated system, we can transform it in different forms, but we cannot destroy it. The sum of energy is always the same in an isolated system. Here we don't have it isolated. We heat it up from outside, but to make it clear. That means the sum of the energy, of internal energy now is U. It is the Q, internal energy, heat, and the work which can be done in the system. This is how to transform these sentences in a mathematical equation. The U, this is the internal energy. The Q is the heat of the system. And the W is the work which can be done. So the delta of that in an internal or in an isolated system is 0. That means delta U is 0 in an isolated system. That is what we wrote here. It can be transferred from heat in work or from work in heat, but the sum of all internal energies in an isolated system is always the same. The delta is 0. What does it mean? a perpetuum mobile is not possible. Huh? It could not provide work in a system, an isolated system, forever when you are not adding energy at any time. When all the internal energy is transferred into work, it stops. Some students come with very good ideas, looking like a perpetuum mobile, but that is not possible. This is, at the end, the reason for perpetuum mobile not possible. Because that would mean we do not have to invest any energy in some isolated system, but it is delivering work. It's working, or any kind of work, but that's not possible without invest of new forms of energy. When you look to a gas turbine producing electrical power, how does it work? A turbine, a gas turbine producing electrical power. Yeah, so first of all, you burn gas. The gas is used to heat up water for the production of hot steam under pressure. And then you decompress it on the turbines, the hot steam, and they start to rotate. Then you have a generator rotating, producing, like in the dynamo of the bike, electrical power, and then you have the electrical power. It works as long as you invest energy in form of natural gas. When you don't have natural gas, it couldn't work. Because the energy comes from the internal energy of the methane molecule, the natural gas. Again? Yes, of course. Yeah. What is nuclear fusion? Maybe you explain it with your words. What is nuclear fusion? So the most well-known or important nuclear fusion is happening in the sun. In the sun, what happens there? The sun is a hydrogen star. The main mass of the sun, 75% of the mass of the sun is hydrogen. Something like 23% is already helium. What do you know about hydrogen and helium? Helium is the next element in the periodic table. It has 2 protons, and hydrogen has 1 proton. So what we do is we create out of smaller molecules a bigger one, and that is not a chemical reaction now, it's a nuclear reaction, because here not the electrons are responsible for that, which is chemistry. Here, the core of the atoms is reacting. Hydrogen protons are forming helium, bigger nuclei in form of helium. And to understand this now, we need the parameter which is called the binding energy of the particles in the nucleus. And the binding energy is delivered by fusionating hydrogen atoms to helium. The most stable elements in the periodic table, I think I talked about. What are they? The most stable elements in the all over table of elements. No. The most stable elements in form of these stability of elements is in the middle of the periodic table, the nickel and iron, Ni-Fe, nickel and iron. That's why we have it in the nucleus of our planet, in the middle of our Earth. We have a high pressure, we have high temperature, millions of years old. The most stable elements there we will find is nickel and iron. So here they are from the binding energy of the particles in the nucleus on the lowest level. And hydrogen has just one proton. And helium has two. And when we fusionate hydrogen to helium, the binding energy of the particles in the nucleus is delivered. Helium is already more stable. And the bigger one are even more stable. The biggest difference between those two energetic levels is between hydrogen and helium. We look to the difference. Of course, the more stable are nickel and iron, but here the difference between others is quite low, but from hydrogen to helium, the step is very high, other way around. From hydrogen to helium, it has a lower level in the binding energy. And this is what we can earn. That's more physics or nuclear chemistry or nuclear physics, but it is an energetic level as well, but now not in form of chemistry. Here we talk about the binding energy of the particles in the nucleus. Is that the answer? Yeah. It's the same theory, huh? Qualitatively different, because here really a lot of energy can be created or earned, not created, earned. In the sun, it's in the core of the sun, we have a temperature level of 40 million degrees Celsius. It's quite hot. In the surface of the sun, we have 6,000 degrees Celsius. It takes a while until it is coming from the core where the nuclear fusion happens to the surface. And from the surface, the emission of energy starts in form of light to the universe, in all directions of the universe. Part of that hits our planet Earth, and that's good. Then we have daytime and energy from the sun, which can be used for photosynthesis and even for a lot of other things. So sun energy, even in the renewables, is the most important one. Just look how to transfer it in a form that we can use it. We cannot create, we cannot destroy, we just can transform it into electrical power, into biomass, into whatever. Biomass we talked about here, photosynthesis. It's a transformation of energy, of light in molecules. And in the molecules, the sun energy is stored. Other questions? So, well, enthalpy, we talked about enthalpy already. The letter is H, and this is now the internal energy and the part of PV. When we talk about a gas, for example, we know we can increase the pressure, then we have more energy. But that comes from outside. That's another form of investing. So the enthalpy is internal energy plus PV. In a chemical reaction, the delta H, we do not know the absolute level of enthalpy. We just can compare. We say the enthalpy of biomass compared to the enthalpy of the CO2 and water, there is a difference. And what we can measure is just the difference. We cannot measure the absolute level. We don't know. We say just, okay, we see a difference. And we can measure it in form of heat. So we say the delta H is the heat of a reaction. Of course, the unit is kilojoule over mole. We already mentioned that. We always normalize everything on 1 mole because then we can compare. Is the energy of 1 mole of glucose more or less to the energy of 1 mole of methane gas? And then we have a relation. We always look to 1 mole because when we have 1 million mole of methane gas and only 1 mole of glucose, okay, then we cannot compare. So, a little example. When we burn pure carbon, so we look to the combustion of pure carbon. What happens when we burn pure carbon? Thinking about the chemical equation for this process. Combustion, oxygen, we need oxygen here. And what is the product? CO2. Is it exothermal or endothermal? Huh? When we burn coal, what is produced? Heat. So it must be exothermal. And we know the value, the delta H of this reaction at 0 means this is the pressure level at sea level, and 298, this is 25 degrees Celsius. That are the conditions here. And now we know the level is minus 393.8 kilojoule over mole. This is what we know. So we create heat when we burn carbon, produce carbon dioxide, and that's the amount of the heat produced for 1 mole carbon. In this case, no water is produced because there is no hydrogen available in the pure carbon. When we have a hydrocarbon, a biomass burning, it's always a hydrocarbon, then even hydrogen is produced. If you have fossil fuels, most of them are hydrocarbons, except without the carbon, pure carbon, that's just the carbon. So only CO2 is produced. Now I say, okay, another option is not total oxidation. This is total oxidation. That is the total oxidation of carbon. We produce CO2. Now I say it is another opportunity just having a partial oxidation, and the product now is carbon monoxide. That's a partial oxidation. This is a very poisoning gas. CO, be aware. CO, immediately if you inhale it, you will die. That's really a problem, CO, because it's blocking the fixing point of the iron for oxygen in the hemoglobin. You know, hemoglobin is responsible for the oxygen transport in your body, in the blood. And it works like in this complex where iron sits in the middle of the complex in hemoglobin. The oxygen is fixed to when we inhale, air, we inhale oxygen, and then it is transported, because fixed to the hemoglobin, to the place in our body where we need it. Most of the oxygen is needed in the stomach for the digestion of our food, which is a kind of combustion. We eat hydrocarbons, meat, salad, bread, whatever, all is a kind of hydrocarbon. And then it is digested. It's a kind of oxidation. And we exhale CO2 and